Have you ever, like, really stopped to think about time? I mean, we live by it, right? We measure it. It feels totally fundamental.
Absolutely. It seems like the bedrock of everything.
But what if I told you that for physicists, especially, at the cutting edge, time is actually a huge headache?
It really is. It behaves so strangely in our deepest equations. It's
Yeah.
almost, yeah, an anomaly.
So today, we're doing a deep dive into something pretty revolutionary. It's a new paper by David Deutsch and Chiara Marletto on what they call the constructor theory of time.
Mm-hmm. A really fascinating approach.
Yeah, and our mission really is to unpack how this theory might just radically redefine fundamental physics.
It's a big claim.
Totally. Imagine if time itself wasn't, built in from the start, but instead things like duration, change, they emerge from something more basic.
Like from what's physically possible and impossible to actually do.
Exactly. Like the river of time isn't just there, it flows from the landscape of possibility itself.
Wild, right? And it's not just philosophical noodling, is it? This
Mm.
problem of time has been a real sticking point in physics for a long time.
Oh, yeah.
Definitely. Think about quantum mechanics. Time isn't something you can measure like, say, energy or position. It's just there,
Yeah.
an external dial telling things when to happen almost.
Right, not really part of the quantum system's own stuff.
Precisely. And then you look at general relativity. Okay, time is woven in with space. It's dynamic space-time, which sounds better.
Yeah, that sounds like progress.
But then measuring time still relies on having clocks, physical clocks. So you end up in this conceptual loop.
Ah, okay. Clocks define time, but time defines how clocks work.
You got it. It's like a dog chasing its tail.
Yeah.
And it strongly suggests that maybe, just maybe, a truly deep theory needs to be timeless at its very foundation.
Okay, let's dig into that. In our everyday lives, time feels like this constant flowing river. Easy peasy.
Very
And
intuitive.
you're saying in physics that river metaphor just evaporates. What exactly is the core problem with how time shows up in our big theories?
Well, traditionally, in classical physics, time is often treated like just a number changing, a parameter, like a stopwatch running in the background, totally separate from the system. It's timing.
Okay.
But then you hit quantum mechanics, and suddenly that stopwatch isn't something you can observe in the quantum sense. It doesn't have its own operator, its own quantum description. It just ticks without any real dynamics of its own,
You just advances but doesn't do anything.
pretty much. Then, yeah, with general relativity, space-time is dynamic.
Mm.
But if you want to measure proper time, the actual time someone or something experiences, you always come back to needing a physical clock.
Right, the clock dependency again.
Exactly. So you get this paradox. How can time itself emerge from the universe's dynamics if the description of those dynamics already uses time?
I see. It feels like you're assuming the thing you're trying to explain.
Precisely. It really hints that a more fundamental theory needs to step outside of time altogether.
Okay, so if the old ways are stuck, how does constructor theory offer a way out? This is where it gets really interesting, right? It sounds like a totally different way of thinking.
It absolutely is. The really core idea, the central assertion of constructor theory, is that the fundamental laws of physics, they aren't about how things change over time.
Okay. So what are they about then?
They're about what transformations are possible versus impossible to achieve, period.
Possible versus impossible. How?
Using these idealized devices they call constructors. Think of them as perfect machines that can perform a specific task with complete accuracy and reliability without ever failing. If a task can theoretically be done perfectly like that, it's possible. If not, if there's any fundamental limit, it's impossible.
And the laws just state these possibilities.
Yes. And crucially, these laws, these statements about impossible transformations, they cannot refer to time at all. They're timeless statements.
Whoa, okay, so that's like the mirror image of the old problem, isn't it? If time isn't in the fundamental laws, how on earth do you talk about change? Or things happening? Or anything evolving? Doesn't that gut physics of its core subject?
That is exactly the challenge the paper tackles head on. How do you get change, dynamics, duration, all of that out of a system based purely on constructor theoretic rules?
Yeah.
Rules about possibility.
Right. How does the river start flowing if the landscape doesn't explicitly include a riverbed?
Good analogy. Now, this approach, it does share some family resemblances with other timeless physics ideas where time isn't fundamental but emerges.
Okay.
But what makes constructor theory maybe unique, or at least very broad, is that it's designed to be independent of any specific theory of matter or space-time. It doesn't assume quantum mechanics or general relativity are the final word. It's trying to be a more foundational layer underneath all that.
Okay, before we get to the magic trick of pulling time out of the hat, we need to get this new language straight. You said possible and impossible. What does that mean very precisely here? And what exactly is a task?
Right. Precision is key here. So a constructor is this idealized perfect machine. Accuracy means how close the actual output is to the desired output. Reliability means it can hit that accuracy target every single time.
Okay.
A transformation or task is possible if there's no finite limit on how accurately and reliably some approximate constructor could eventually perform it. You can always, in principle, build a better machine to get closer to perfection.
Got it. And impossible.
Impossible means there's a fundamental limit. No matter how hard you try, you can never build a constructor, even an approximate one, that achieves it with perfect accuracy and reliability. It's just fundamentally disallowed by the laws of physics, expressed in this possibility language.
Okay. And a task.
A task is basically the job the constructor does. It's defined as transforming a physical system, they call the system the substrate, from some initial state, let's call it X, to a final state, Y.
So input X to output Y on substrate P.
Exactly. And for the task to count as properly defined, there has to be some measurable way to know it's finished, like a flag going up or like a computer program halting.
A definite endpoint.
Yes. And importantly, it's deterministic. A task is either possible or impossible. No middle ground, sometimes it works. Also, these constructor laws, they don't specify the universe's initial conditions. And crucially for us, the duration of a task. It's simply not specified in the task definition.
So the timelessness is baked right into the definition of a task.
Precisely. That's how it starts to sidestep the traditional problem of time.
Okay, this raises a big question for me. How do these possibilities combine? Like, if task A is possible and task B is possible, what does that mean for doing both?
Yeah, that's fundamental. There are two key principles governing this. First, the composition principle. It basically says, if task A is possible and task B is possible, then performing them in sequence or combining them must also be possible.
Seems logical. Like, if you can melt ice and you can boil water, you should be able to melt ice and then boil the resulting water.
Exactly. The composite task has to be possible if the individual components are. If AB is possible and CD is possible, then doing both, maybe represented as ABECD, must also be possible. Even the simplest composition, the null task, represented by an empty set which does nothing, must be possible.
Okay, the null task, we'll come back to that. Sounds important. What's the second principle?
The second one is locality. It states that if you have a composite system, say made of two parts, A and B, then performing a task only on system A cannot change the attributes of system B.
Right, acting locally on one part shouldn't magically affect a separate, untouched part. Seems obvious, but maybe it has subtle consequences.
It really does, especially when you bring in quantum mechanics. They give an example. Right. Imagine you have a set of quantum bits, qubits. A certain task, let's call it F, might be possible to perform on each individual qubit separately.
Okay, you can do F on qubit 1, then F on qubit 2, and so on.
Right, so F on Pn is possible for any n. But performing that exact same task, F, on the entire set of qubits simultaneously using a single constructor, that might be impossible.
Why?
Because doing it simultaneously to the whole collection might violate a larger quantum rule, like unitarity, which governs how the total quantum state evolves. It shows a crucial difference between something being possible individually versus collectively.
Yeah.
Locality helps define these constraints.
So, okay, if everything is framed in these timeless possibilities, how do we pin down something as simple as unchanging or isolated? Usually we think of those in terms of time, right? Something doesn't change over time. How does constructor theory do it?
Yeah, this is where you really see the paradigm shift. An isolated substrate in constructor theory isn't defined by not interacting dynamically over time. Instead, it's defined purely by possibility. It's a substrate where the possibility of any task being performed on it by itself depends only on its own attributes. Nothing external influences what can be done to it.
So its potential for transformation is entirely self-contained.
Exactly. And then building on that, you can define a static attribute. This isn't just something that happens to stay the same. It's an attribute that is fundamentally impossible to change if the substrate is isolated.
Impossible. So much stronger than just being, say, conserved energy.
Much stronger. Total energy might be conserved, but you could still, hypothetically, perform a task that shifts that energy around within the isolated system, changing other attributes. A static attribute in this constructor framework is truly immutable as long as the system remains isolated. No possible task performed only on that system can alter it.
Now, this is fascinating. You mentioned the null task earlier. How does something seemingly so abstract a task that does nothing lead us towards the concept of a clock? Walk us through that connection.
Right, the null task. Remember, it's represented by the empty set. It has zero constraints, doesn't specify a substrate, an input, or an output. It's the ultimate easy task.
Okay.
And by the composition principle, because of the composition of zero tasks, it must be possible. Therefore, a constructor that performs this null task,
Yeah.
a null constructor, must be constructible.
A machine that reliably does nothing.
Sort of. But here's the critical step.
Yeah.
Since the null task doesn't act on any external substrate, the null constructor itself must be an isolated substrate. It operates entirely on itself.
Ah, okay. It's self-contained.
Exactly. Now, for this isolated null constructor to work as a timer, it needs some internal machinery. Specifically, it needs at least 3 distinct attributes. Since the null task doesn't specify an output, the indication that the task is done has to be an attribute of the constructor itself. Let's call this the halt flag attribute, maybe label it 1 for completed.
And this one state has to be special.
It must be a static attribute, according to the definition we just discussed. Once the timer hits 1 fled, it has to stay there, because that's the signal it's finished. It can't accidentally revert.
Okay, a stable, halted state. What else?
It needs a distinguishable starting state. Let's call it 0. This one has to be non-static, something you can reliably prepare the timer in. And then it needs at least 1 intermediate state, let's call it R for running, which is also non-static, representing the time between start and finish.
So 0, R1, start, running, stop. And the stop state 1 is static.
Precisely. Those 3 attributes, 0, R1, with 1 being static, are the minimum requirements for a null constructor to function as a basic timer.
So these 3 attributes, 0, R, and 1, essentially define a timer in constructor theory. How does that work in practice? And how do we then get our familiar ideas like specific durations or even synchronizing different clocks?
That's exactly right. A timer is a null constructor with this specific structure, 0, R1, with 1 static, plus that distinguishable halt flag. The actual duration isn't explicitly put into the constructor's definition. It's sort of implicit in the possibility rules governing its transition from 0 to 1.
Okay, so the duration emerges from the possibility rules.
Yes. And for any physical theory to be compatible with clocks and time as we experience them, it has to obey certain constructor theoretic conditions regarding these timers. This is where formulas 8 and 9 in their paper come in.
Right, what do they say?
Essentially, formula 8 says, if you take 2 timers designed for different durations, say T's and T, where T's is longer than T, and you start them both at 0, 0, then the task of getting them both to the halted state must be impossible.
Ah, so you can't force the slower clock to finish at the same time as the faster one. They have to respect their built-in different possibility pathways.
Exactly. It ensures their distinctness. No external constructor can just speed them up or slow them down arbitrarily to make them agree.
Okay, makes sense. And the other formula?
Formula 9 says the opposite. You take 2 timers designed for the same duration T, then starting them at 0 and having them both reach umbra 1 simultaneously must be possible.
Okay, so clocks meant to have the same duration can be synchronized.
Precisely. This possibility defines an equivalence class all timers for which the simultaneous 0, 0, 0 long transition is possible belong to the same duration T. This is the foundation for the synchrony of clocks, even if they are isolated from each other.
Wow. Okay, let me see if I've got this. This is how we derive the very idea of time and specific comparable durations from a theory that never mentions time in its basic laws. It just falls out of the rules about what's possible and impossible for these special null constructors.
You've got it. That's the core insight. Time isn't fundamental. The possibility of constructing reliable timers is. A physical theory supports time if and only if it satisfies these constructor theoretic conditions about timers.
That's mind-bending.
It is. And it has further implications. For this synchrony to work, like we see in the real world, especially considering relativity where motion affects time, it implies that things like the state of motion or the space-time region of a substrate must themselves be treated as attributes, or maybe even additional substrates within the constructor theoretic laws.
So the laws of possibility have to somehow incorporate information about motion and location to get relativistic time effects right.
Exactly. It suggests how deep this framework might need to go, potentially even defining the rules for space-time itself in terms of possible and impossible constructions.
Okay, so we've used possibility and impossibility to build clocks and get a notion of duration. That's huge. But how do we get back to dynamics? The idea that things change continuously, that systems evolve. Physics is full of differential equations describing how things change smoothly over time. How do you recover that from this timeless foundation?
Right, that's the next crucial step. Recovering dynamics. It actually follows quite elegantly. First, you define what you mean by a real variable v in the system. It's essentially a set of non-static attributes, let's say v, indexed by some parameter. Think of v as just labeling different states the variable can be in.
Okay, so v represents the state of our system related to this variable.
Exactly. Now, consider a composite system. Our substrate P, which has the variable v, combined with a timer C that has some duration, let's call it E, corresponding to the change of the parameter.
So the system we care about plus a clock.
Yep. Now, if the task that takes the combined system from an initial state, meaning the system has attribute v, and the timer is at start to a final state, 1, meaning the system now has attribute v plus v, and the timer has halted if that task is possible.
Which means it can reliably happen.
It means the system P can reliably transform its attribute from V to V plus V precisely as the timer C completes its cycle.
Okay, so the change in the system is tied to the ticking of the timer through possibility rules.
Exactly. And now for the magic. Consider the ratio of the change in the variable to the timer's duration parameter, V plus VV. If you look at the limit of this ratio as the timer duration gets infinitesimally small, which corresponds to using shorter and shorter duration timers.
You get a derivative.
You get the derivative.
You have a derivative.
You can recover the differential equations that describe the continuous evolution of the variable v relative to the progression parameter defined by the timer.
So dynamics, the smooth change we see described by calculus, emerges from the possibility of making incrementally small changes linked to incrementally short timer durations.
Precisely. It shows how the familiar machinery of dynamics can be reconstructed from these more fundamental, timeless principles of possibility and impossibility.
Okay, putting this all together now, connecting it to the bigger picture. You mentioned earlier this isn't the very first timeless idea in physics. So what makes this constructor theory approach really different, or maybe more fundamental, than those other attempts?
That's a really important point. You're right, other timeless formulations exist, particularly explored in the context of quantum theory and the search for quantum gravity. But often those approaches tend to assume certain things.
Like what?
Well, they might presuppose that good clocks are possible, or they might assume the principle of locality holds, or they might rely on the existence of certain kinds of information processing systems from the outset. They often build upon existing dynamical frameworks, but try to remove time explicitly.
Okay, so they start closer to the physics we know.
Kind of, yes. Constructor theory, as Deutsch and Marletta presented here, tries to start further back. It doesn't assume those properties are given. Instead, it aims to provide an explanatory foundation for why those things, like good clocks and locality, should hold in a physical theory. The conditions we talked about for timers, like formulas 8 and 9, are proposed as fundamental laws themselves, derived from the deeper principle of possibility.
So it's not just removing time, it's building up the possibility of time-like behavior from more basic axioms about what can and cannot be done.
Exactly. It's offering a basis for dynamics and time, rather than just reformulating existing dynamics without time. And another crucial point is its breadth. The framework is general enough that it logically allows for theories that are constructor theory compliant, but do not support timers.
Meaning universes where time as we know it just doesn't emerge?
Potentially, yes. It opens the door to thinking about physics that might operate under fundamentally different rules, perhaps relevant in extreme conditions like inside black holes or at the Big Bang, where our current concepts of time break down anyway.
Wow. Okay, so we've really taken a journey here from the strangeness of time in standard physics, this sort of paradoxical behavior,
The problem with time.
to this completely new paradigm, constructor theory, where time and dynamics aren't fundamental, but they emerge from what's possible and impossible to construct. It's genuinely a mind-bending perspective on the universe.
It really reframes things, doesn't it? This deep dive suggests that the flow of time, the very experience of change that feels so basic to us, might actually be a consequence, an emergent property rooted in the fundamental rules of what operations can and cannot physically happen.
Reality based on capability.
In a sense, yes. What can be brought about?
So, to leave you, our listener, with something to chew on, consider this. If time itself isn't fundamental, if it's a consequence of the universe's task list of possibilities, what does that really imply about the ultimate nature of reality? And maybe more intriguingly, what other concepts that we currently think of as absolutely fundamental might also just be emergent properties waiting to be explained by a deeper layer.